as we continue to talk about sound, we have to talk about hearing as well. First, sound is characterized by pitch, the frequency, as we talked about just a little while ago, and loudness. Pitch is our sense of frequency of the wave. Human hearing ranges from about 20 Hz to 20,000 Hz. We call infrasonic frequencies that are below 20 Hz. These are the frequencies that are caused by earthquake, thunder, heavy machinery, and some animals communicate with them, like elephants. Ultrasonics are frequencies that are higher than 20 Hz. They are used for medical diagnostics, and some animals also can hear ultrasonics. Bats, for example, can hear up to 100,000 Hz. Loudness is related to the intensity of the wave. Okay, what do we mean by the intensity of the wave? Intensity is the power per unit area. Power. Power, remember, is related to energy. Unit is watts. Watts being joules per second. For a wave, power is proportional to the amplitude of the wave squared. Okay, whatever the amplitude of the wave squared, power is going to be proportional to it. What we define as the intensity is power over the area, power per unit area. So in other words, if I have an amount of power passing through this window here that I drew, if we divide that power by the area of that window, we get the intensity of the wave there. So the unit is watts, the unit of power, divided by meter squared. As a guidance, we have what's called the threshold of hearing. That's the minimum sound that we can hear, I sub 0. It is 1 times 10 to the minus 12 watts per meter squared. In the opposite side, we have what we call threshold of pain, something painful to hear, and that's 1 watt per meter squared. Look at the orders of magnitude. We go from 10 to the minus 12 to 1. That's 12 orders of magnitude difference. Essentially, that tells us that we are capable of hearing a huge range of loudness. We can do that because our perception of loudness is logarithmic, it's not linear. It's not going to compare the values in a one-to-one level. Okay, we'll talk about that in a little bit. So, logarithmic decibel scale. So our perception of loudness is not linear. So it follows what we call a logarithmic decibel scale. So our ear does not distinguish very easily different I's. However, it distinguishes various decibel levels that we denote by betas here. And beta is defined by 10, and we put here dB, 10 dB times log of the base 10 of I over I0. I0, remember, is the threshold of hearing. That's the 1 10 to the minus 12 watt per meter squared. So that's what our ears are going to perceive. The decibel level, which is, again, 10 dBs times log on the base 10 of the ratio of the intensity of the sound to the threshold of hearing. So the difference between two sound levels, beta 2 minus beta 1, is going to be 10 dB log of the base 10 of the ratio of the intensities. Now the intensity level is really dimensionless. The dimensions get cancelled when we take the ratio. But we usually use dB as a reminder that we are talking of that scale. This is 10-based log scale, not natural log. In your calculator, you might find something labeled as log n, that's the natural log, and log base 10 is usually written as log.